looking at the first set of calculations, let me just read some of the instructions. Okay, so you're doing the following before you do the report template. You really can't do the report until you have the results, right? It's not going to make sense for you to report anything if you don't have final values. So the calculations is where we start. So the rule that you want to apply throughout the calculation section is that you really only need to show me one solution per section. So you have several trials, right? 6 trials. You only need to show me the written solution, like step by step for one trial, but you give me the answer for all of them. Does that make sense? Okay, so standard, and another thing is make sure to show all your units and box your final answer. Okay, so standard solutions. You can write in pencil if you'd like. Usually I have pen, but I don't even understand why I did that in the past, pen. So let's just use pencil here. In case you make a mistake, you can go back. So we're under the section that says standard solutions, number 1. It says calculate the initial molar concentration of thiocyanate after mixing. And then I give you an example for trial 1. So the example that's given to you is just your M1V1 equals M2V2. Does anyone have a black dry erase marker? Because I gave some people. Will you just throw it? Thanks. Okay, so M1V1 equals M2V2 is really what's being applied for all of the calculations concerning concentration. So when I'm calculating concentration after mixing, this is what I'm using to apply that. So the example that I give, it says 0.0020 moles of thiocyanate, or moles per liter of thiocyanate solution. And then it's multiplied by 0 liters of thiocyanate. So where did these numbers come from? I give this 0.0020 moles per liter of thiocyanate, and I multiply that by 0.00 liters of thiocyanate. Where did these two numbers come from? Yeah, so if you look at your table 1, so I'm scrolling, flip back to table 1 for the standard solutions. And so you did this calculation for the pre-lab, right? Didn't you? Which pre-lab question was it? Number 2? It was number 2. So go back, see how you did that calculation, then take all those numbers and input them as your answers for trial 2, 3, 4, 5, and 6. Okay? Or for, did we call them trial or run? Or solution. I think we called them solution. Solution 1, 2, 3, 4, 5, and 6. So just to reiterate how we got these numbers though. So I'm looking at table 1. So these numbers are from table 1 on page 1.5. Page 1.5. Okay, this number right here, if you look at the top of the table, that's the concentration at the very top. So this right here is your M1, right? It's the initial molarity or the stock solution molarity that we used. This number is the number right underneath that for solution 1. So that's the volume that was used. This is V1. So I multiplied M1 times V1, okay, to get a value, which was 0.00 moles of thiocyanate. So again, I'm using that example calculation on page 1.9 to give me this answer. So 0.00 moles of thiocyanate. Are you guys following so far? Any questions? Yes. Okay. Going back to the calculation section just to see what the example again. I took that number, so this 0.00 moles of thiocyanate, and I divided it by 0.0500 liters of solution. Where did that number come from? 0.0500 liters of solution. That was my what? My total volume, right? That was the final volume on the very right-hand column for table 1. So I divided this by 50 milliliters, also known as 0.05 liters. Okay, this number right here then is what in this formula? What's this 50 or 0.05 liters correspond to here? Your V2. So this is V2. So if you divide that, that does give you M2, which in the case of the first trial is equal to 0. So M2 for the first trial is 0.000 molar. Okay, that's what you should have gotten for your pre-lab question. For the calculation section, you are going to show me that solution one time. Okay, you can choose whichever trial. You could do it for this trial if you just wrote it down. You could do it for the second solution, whatever. But you need to show it all the way through with all units, how they cancel, etc. for one trial or one solution, and then give me the answer for the other solutions. Does that make sense so far? Okay. If you notice, I'm going to let you finish that, fill those in for all trials or all solutions. And then as a group on your table, you're going to work on number 2 to establish what your answer for number 2, what that is together. I will give you probably about 5 minutes to finish 1 and 2, and then we will jump in together. Okay? What's your answer for second solution? 0.004 or something like that?
Something like that.
Thank you. Oh, it's -5, really? Is that for saying -5? Okay. Okay, so for example, this is what I'm looking for number 1. One of your trials, it doesn't have to be the first one, or one of your solutions, it doesn't have to be the first one, needs to show the entire calculation with units that cancel. So you're left with moles over liter, which is molarity for thiocyanate. Okay, so that was the first solution, 0 molar. And then for number 2, number 3, number 4, number 5, and number 6, you just need to give me the answer with the correct sig figs. All right? Okay, what about number 2? So I left you in your table to kind of discuss number 2. It says determine the equilibrium molar concentration of the product. This requires thought but no calculation. I heard at least a couple of tables talking about this. How do we determine the molar concentration of the product? It's going to be based on one of the values that you already calculated. Remember, one of them in table 1 is the limiting reactant. That's the one that determines what the product concentration is. So which one is the limiting reactant for table 1? Yep, it's the sodium thiocyanate. So that's limiting reactant, which means all of your sodium thiocyanate is going to become the product. So therefore, your answers that you just put down for number 1 are the same as your answers for number 2, right? Because all of the limiting reactant became the product. So whatever you got for T1, for number 1 is the same as your answer for T1 for question 2. So question 2, T1 would be equal to 0.00 molar. T2 then would be equal to 4.00 times 10 to the negative 5 molar. Because remember, all of your sodium thiocyanate converted into the product. So whatever you calculated for number 1 is the same as your answers for number 2. So you don't need to show that calculation. Just write the answers down. Does that make sense? Okay. All right, let's look at a Beer's Law plot. So that's number 3. We're going on to number 3. If you aren't finished writing down all your values, that is okay. You can go back and finish those later. But it says prepare a Beer's Law plot for the product using your answers from number 2 above and the absorbances written in data table 1. So you have your Beer's Law plot. It should look something like this, or the graph paper that you have as a part of the lab handout. So I don't think I labeled the axes. No, I just gave you a blank kind of graph paper. So go ahead and label the axes. Your y-axis, which is your dependent variable, the information that you got from the spectrophotometer, will be right here, ranging from your minimum to your maximum absorbance values. So I think if I remember correctly, most of your maximum absorbance values for data table 1 was around like 0.8, but can you guys check that? Look at your data table 1 absorbance values. Is that, okay, that's right, Jordy says, yeah. So it wasn't that much higher than 0.8. Some people might have gotten 0.6, but I don't think I saw anything higher than 0.8. So I just started at 0.1 as my lowest value after 0, and then every tick mark was 0.1 more than that. I would use as much of your graph paper as you can, right? You don't want a tiny little line on this giant graph paper. You want it to span the entire area. The point of a graph is so that you can see the trend or relationship between the x and the y. If you just have a line that ends up like this, that doesn't tell anyone anything, okay? And I have seen that many times. So go ahead and label your y-axis. We'll work on the x-axis in a second, but it will be concentration of your product. So do the y-axis first, label that, make sure you give it a name, put numbers at appropriate intervals. And I'm going to walk around. I haven't talked about the x-axis just yet, but you can do that if you like. Okay, so it is going to be concentration. Some of you wrote it as decimals. You could also write it as in scientific notation. So look at your concentrations that you just wrote for number 2. You want the graph to reflect the minimum to the maximum of your concentrations for number 2. So your minimum obviously is 0, right? Your minimum concentration. Your maximum is what? What's your highest concentration for number 2? Or for number 1, they're the same. 2 times 10 to the negative 4. So I saw some decimals which went from 0 to 0.0002, which is sometimes a little hard, right, to write on this. So if you do it in scientific notation, you could start with 2, or let's start with 4 maybe, because that's your first one. 4.0 for this one, which is the same thing as 4 times 10 to the negative 5, right? You're applying this scientific notation right here. The next interval could be 8.0, then we could do 10, then 12, then 14, then 16, then 18, then 20. Okay, this right here, 4 times 10 to the negative 5 is the same thing that you got for your second concentration, right? Do you see your second concentration in number 2? Look at your answer to number 2, because some people's eyes are glazing over. So I'm giving you really specific instruction. Look at your second concentration for number 2. Is it 4 times 10 to the negative 5? Yeah. Okay, so that's why I put that right here. 4, and this means I'm taking that value times 10 to the negative 5. So I know for those in the back it's kind of hard to see at the bottom. Here, let me write what I wrote there. This is FeNCS 2 plus, and then I put that it's molarity, and it's going to be times 10 to the negative 5. So I'm just saying all these numbers right here are multiplied times 10 to the negative 5. And your last concentration, your highest concentration is 20 times 10 to the negative 5, also known as 2 times 10 to the negative 4. Okay, lots of scientific notation in there. So this, if you wrote exactly what I did, and then you made sure to note that all of these values are times 10 to the negative 5, that will span your concentrations perfectly. Everyone around you has different absorbance values, but they have the exact same X values, exact same molarity. So your X axis should look the same as everybody else. Okay, so again, you've set up your graph. You have your x-axis, you have your y-axis. Now you're going to start plotting your values to make your Beer's Law plot. So where do those numbers come from? Your x values are up here. So these all in number 2, your answers for number 2 are your x values. Your corresponding y values are the absorbances that you got in data table 1. So these right here, y values are in data table 1. So let me ask, I'll ask Hector if you do have your data in front of you, that I could ask you what the absorbance value is. Okay, so let's just start with T1. So your first solution, right? Your first solution had a concentration of what? What concentration did you get for your first solution? 0, right? Okay, so his first X value then is 0. So X, Y values, his first one is 0. And what's your corresponding Y, or your absorbance value for that first solution? That was your blank, right? So it's also 0. So his first is 0, 0, which means you have a dot right here, right? That's 0, 0. What's your second X value? So second X value is 4.00 times 10 to the negative 5. And the corresponding Y value is? Say it real loud.
0.145.
145. Okay, this right here, what I'm going to box, that is Hector and Felipe's second XY value. This number for you should be the same. The concentration should be the same for your second XY value. But your Y value should be different, right? You have a different absorbance in your data table 1. Okay, so yours, Hector, would look, let's erase this. So So I know I'm at 4.0. I probably should have put this somewhere else. 1.5. So I'm plotting x and y value number 2 at 4.00 times 10 to the negative 5 molar and 0.145. So I'm right here, and I'm about right here. This is about 0.145. So this would be his second data point. Again, at 4.00 times 10 to the negative 5 and 0.145. Does that make sense? Okay, so you're doing that for all your data points to get a trend line. Okay, it should be straight, may not, right? Your trend line might be a little crooked, but it should be a rather linear relationship. So that's your next task, is to work on your Beer's Law plot. We will need that plot in order to do anything with the equilibrium values. We can't, if we don't have this, then we really can't move on. So go ahead and start plotting that, and I'll walk around, you stop me if you need me. What was that? I think that is correct. Okay, so I'm going to pretend like this is my graph. You have your graph in front of you. Now we're going to start using it. Well, in a second. Okay, the next page, page 11, looks at equilibrium solutions. So this is equilibrium solutions number 1. It says calculate initial molar concentration of thiocyanate again after mixing. But this is for table 2. So if you look at table 2 in your procedure, you're going to do the exact same calculation that you did over here, but you're just going to use different numbers, okay? So do that calculation so you have that ready. Again, you're only going to show me one solution and then the rest of the answers, and then we will jump to number 2. Actually, I'll say this. Do 1 and 2. Do number 1 and 2. They're the exact same. Do number 1 and number 2.
Professor?
Yes.
Why don't you
This isn't. Well, I mean, you would take these and convert them to tables, but you wouldn't do it in a table because the table represents.
Oh, okay, so you don't have to.
You don't have to.
Yeah,
Okay,
yeah,
no.
I work every other
Okay.
Saturday. Yeah, I was good. We could even,
Wait, so since we have to do like the same calculation for table 2, do we have to like for one of them do the whole process again, or can we just
Yeah, like this, you'll do it one time.
one
Yes.
time and then?
Yes.
Thanks.
Yes, you're welcome.
oh, really? When was that?
I think they are the same numbers, right?
Yeah, is that the same
Yeah.
numbers?
But the iron changes. But yeah, the thiocyanate I think is the exact same. Except for your total volume, right?
Oh,
Yeah.
okay, great.
I think that's right. So I'll show one example for number 2 as well. I'll do it for the third solution. And if you have that, you can compare numbers. Oh, for the third solution for iron, they're all the same, right, for iron? Okay. You getting 0.1 or 1.0% to negative 3.
Yeah. For count 2.
Oh, that's right.
2.0.
Yeah. All right, any questions on number 1 or 2 for equilibrium solutions? So for the third solution for thiocyanate, I got 4.00 times 10 to the negative 4. Oh, this should be 1.00, right? And then all the solutions for iron should be the same, right? Because they all have the same volume. All right, so let's look at what we do with those numbers. You have your Beer's law plot, you have your initial concentrations. Now number 3, it says determine the equilibrium molar concentration of the product, okay, which is the iron thiocyanate, using the absorbance data in your Beer's law plot above. The absorbance data for data table 2, right? So it's based on the equilibrium solutions. So let's just look at, oh, that shouldn't be number 3, this should be number 4. Let's say this is number 3 right here. Let's say for trial 2, or for the second solution, Brandon, what is your absorbance value for the second solution for the equilibrium run? 0.166. Shuri, what's yours? Do you have it?
For the second,
Yeah, second data table.
0.170.
Okay, so very similar. So around that value, okay. So it says to take your absorbance value that you have, look at your Beer's law plot, and determine what the concentration is. So I'm going to look at what the concentration is corresponding to 0.166. Okay, So 0.166, this is 0.2 right here, right? So 0.166 will probably be around here. Okay, so I'll say this right here is approximately 0.166. Okay, I'm just gonna dot out or use a ruler to see where this corresponds to on your trend line. Okay, so far, does that make sense? You're seeing where it corresponds on your trend line. Then you're getting your corresponding X value. That's your concentration. Okay? So you take your absorbance, you see where it is on the Y, draw a line, a straight line, hopefully, with a ruler or a piece of paper over to your trend line, and see where that corresponds on the x-axis. So it looks for me, I might say something like 5.8 times 10 to the negative 5. That's my concentration of iron thiocyanate at equilibrium. For trial, what did I say? Trial 2. Okay, so you're going to do that for each one. Now, what I would suggest, though, in the interest of time, just pick one trial or pick one run, because we can use that to basically solve our final value for at least one run or one solution. So I chose the second solution. You could choose the second or the third, something like that, and just get a corresponding concentration. Let me walk around. Yeah. Let me turn this off. Okay, so again, you're using your Beer's law plot from the standard solutions because these are known concentrations. That's how you were able to graph it, right? You knew the concentration and you knew your absorbance values. For the equilibrium concentrations, or for the equilibrium solutions, you didn't know the concentration of the product. Okay, you're unaware. But what you did know is the absorbance values. So you could take those values in your Beer's law plot and say, okay, well, I have this absorbance. What concentration does that correspond to? So you're using the standard solution data to determine what your equilibrium solutions are. Okay, so let's say for my trial 2 or my second solution, I said that I got a concentration of 5.8 times 10 to the negative 5. And that is my FeNCS2+. Okay, so all the numbers that you get for number 3 are the concentration of your product, okay, for different trials. Okay, so number 4, this is where we're applying the ICE table. So it's the next page. It says calculate the equilibrium molar concentrations of thiocyanate, iron 3, and, bless you, iron thiocyanate using an ICE table for each trial. Okay, it says an ICE table is provided for you for trial 2 since the first trial is a blank. Okay. So just look at trial 2. There's an ICE table, and I have one written right here. Okay, we have iron 3, then we have thiocyanate, and then we have iron thiocyanate here. Okay. All right, let's look at I. So I under iron 3. So we're looking right here. What we put in this little cell right here. It says that what you put in that little cell is the answer from number 2 above. So look at your number 2 for the equilibrium solutions. Okay, number 2 is calculate the initial molar concentration of iron. So what did you get for this number 2? So the one with the big arrow. What did you get for the initial concentration of iron? Actually, all the solutions, all the trials should have been the same, right? So what was it? Was it the 1.00 times 10 to the negative 3. Okay, that's what you should put in ICE table for trial 2. All right, now go back to the ICE table. Let's look at thiocyanate. So right here, we're looking at I for thiocyanate. It says answer from number 1 above. So for trial 2 or solution 2, what was your concentration of thiocyanate? think it was, yeah, number 1, right? Number 1 under equilibrium solutions. Is that right? Okay, what'd you guys get for the second solution, T2? Yeah, go ahead.
3.00 times 10 to the negative 4.
Thank you. 2.00 times 10 to the negative 4. Does that look right? Okay. And then continuing on the ice table, it says that iron thiocyanate concentration is 0 at the beginning, right? Because that's before a reaction has occurred. That's what initial refers to. Before a reaction has occurred, it's the big 0 right here. All right, great. Woohoo. Okay, let's move down to C. So I'm still looking at the printout. Under C, for iron, it says minus answer from number 3 above. Okay, so this is kind of like a little puzzle. So minus answer from number 3 above. I can explain this to you in our time, but right now let's just find what our answer from number 3 above is. This is your number 3, right? You used the Beer's law plot to determine your concentration. So this is for my second solution. I had an absorbance of 0.166 that gave me this concentration. So my change then should be minus, like it said, minus my answer, 5.8 times 10 to the negative 5. And that's the same for thiocyanate, minus answer from number 3 above. So minus 5.8 times 10 to the negative 5. I see some. What's going on? So just ask me now if you guys want to figure out any details. Any of your questions are probably going to be someone else's questions. Okay, so help each other out if you are concerned about anything. Giving it a moment. Giving it a moment. Yes. Okay. So question from Victor is, why would this be negative right here? So that wasn't explained in the ice table. This would be negative because you started with no product. So you have to lose reactant. So it goes from reactants to products. Does that answer that? Okay. So if this is minus 5.8 times 10 to the negative 5, this is plus 5.8 times 10 to the negative 5. That's basically your x value that we've been using in our ice tables, except now we know the number. Okay, the number is given to us based on our answer from number 3. Now if there was a 2 right here in front of the iron thiocyanate, you would have to multiply this number by 2, right? It would be plus 2x. So you will see that sum in the future. All right, that's all the information given in the ice table. Now I need to solve for E. Just putting these numbers together. Okay, so you're going to take, for iron, 1.00 times 10 to the negative 3 minus 5.8 times 10 to the negative 5 to get your E. You'll do the same for thiocyanate and for the products. We won't have the exact same numbers, except, did I get your number, Hector? Is that where I got 0.166? Who did I get 0.166 from? Cherie? Did I get? Who did I get it from? Brandon? Did I get it from you?
Yeah.
Okay. Okay. Everyone's like pointing around. Okay. So only Brandon and Andrew and I will have the same number down here, but yours should have the same exponent, or it should be pretty close. So I'm getting 9.4 times 10 to the negative 4. Is that what you guys got when you put it together, Brandon and Andrew? Or did you do it yet?
Yeah,
Okay.
I got decided.
For C? Oh, for this right here? So, okay. So we'll have close.
So yeah, it's not. It's off my like.
0.1. Yeah, I know. Honestly, what we should have done here, if we wanted to make it more accurate, we'd have another decimal place, but since the graph is only on 2 sig figs, then we'll do 2. I would suggest you underline your sig fig. So Andrew, for yours, I would keep that too, but just underline your sig fig. So we'll have 2 sig figs at the end, but I don't want to round just yet. Oops, I missed my multiply times 10. There you go.
So it's fine that I use state and
Use what one?
the it's already before. I had one stuff in it.
Oh, yeah. You can put it in there. Yeah.
It's kind of hard to fit everything.
I know. There's so many numbers. But again, you only have to show the ice table one time. So all the other ones you just calculate. Yeah. Is it this value right here? Oh, right here. I just did this minus this. So I just put these together. These two. Oh. All right, we're down to our last step. So, any questions before we do our last step? I'll leave this up here, obviously. What?
So there's still one more step.
There's one more step? Because the goal was to find what in this lab? The constant, right? The equilibrium constant. All right, so I should have brought candy to throw out. Okay, so we have to use these to solve the constant. Does anyone know, if you can tell me, just off the top of your head from all the knowledge from reading and lecture, etc., if you can tell me how I use these numbers to solve for K, raise your hand, and I'll give you extra credit. Yeah, Diego. Say that again. You don't add them. Yeah, Andrew? Yes, okay, you plug it into the K expression, products of reactants, right? Okay, so let's do that right here in this tiny little area. Papers. So this is number 5, I think? Everyone's like, yes, please be done. Okay, number 5. Okay, this is only going to be for solution 2 for me. K equilibrium. Let's see if this shows. Okay. K equilibrium equals iron thiocyanate at equilibrium over iron 3 at equilibrium times thiocyanate at equilibrium, which is, let's plug in the numbers. what that equals. Okay, I get 430, which is a great number. Whew. Okay, go ahead. I'll post this video too, so you guys can come back and look at it.
Great job.